So we are going to do an AR2 model with repeating roots, and then we can move on to AR3. Once we are done with AR3, we can get into R model. So the next exam, we stopped at AR1. The third exam will be on the 26th, the week of Thanksgiving, Tuesday.
Make sure we're here.
Of course. So,
Wait, isn't it 26th? Are we off that day?
or 25th. It's a Tuesday
No, Tuesday.
of that week.
Is that 23rd? Actually, that's the 23rd. I'm just trying
Is
to.
it-
But that's good.
In the 23rd.
Okay, 23rd.
You're saying 25th is actually Thanksgiving.
You see, that's why. We'll try to go all the way up to Arma 1-1. We will see.
Professor.
Yes.
So last time we did the complex roots, this time we're doing repeat roots, are we just gonna do like normal roots at all, or?
We did a bit. Did we not?
I honestly don't know. I may be stupid, can someone help me check?
Because using normal roots, I mean, we didn't, we can just do the distant roots case also before we get to AR3. So if I'm going to simulate n equals 1024 and AR 0.9, in other words, phi1 is 0, right? If phi1 is 0, the characteristic polynomial will have the exact term 0. Naturally, it will have repeating roots. Okay, everything's going to work. So when you graph this, like the complex roots case where we sort of had an oscillatory pattern, here we're going to have a gentle decay, but you know, lots of significance in terms of the autocorrelation function. If you look at the PACF, on the other hand, the partial autocorrelation function, which starts at 1 and moves on to 2. Clearly, in our model, whatever we have at time t doesn't correlate with t minus 1. So nothing there. It correlates with t minus 2. So we have a peak, and that peak is 0.9. So you can read it directly from the PHCF plot. Are we good? So now our goal is to estimate the value of the coefficients. So the model that I simulated, the true model, is yc equals 0.9, yt minus 2. Of course, there is epsilon t. Yes? In practice, this is where we start. We have a series, we look at the ACF plot, we look at the PACF plot to determine the order of the AR model, excuse me. So we need two autocorrelations if we want to use the Yule-Walker approach. Of course, I was able to recognize the order directly by looking at the PACF plot, but I'm going to use the Yule-Walker method. So the Yule-Walker matrix setup is very straightforward. Row 1, row 2, 1, row 1, row 1, 1, phi1, phi2 from last time. Yes? So we know the values. So 0.022, 0.895, 1, 0.022, 0.022, and 1. Check that matrix outputs, right? I just wanted to be sure. We can call that matrix A, that as B, and the coefficient vector as B. So what we have is A equals B multiplied by B, the coefficient vector. We multiply both sides by the inverse of the matrix B. So B inverse A would be equal to the coefficient vector phi. And I showed you how to do this using a calculator. So give it a try and let's find the coefficient vector phi. So once we hit that, what is the value of the phi vector?
It's 0.002 and 0.895.
Good. So pretty much the estimated model based on this series, because in practice we do not know what the truth is. That's what we're trying to find. So the estimated model in this case will be YT equals 0.002, YT minus 1 plus 0.895, YT minus 2 plus epsilon t. Right? And you may look at that and say, well, the method didn't do right because we didn't get the correct model, right? Can I say that? That I did not get the correct model, I did not estimate the correct model.
Isn't it pretty close to 0.9?
Okay, but the true model doesn't have YT minus 1.
Well, that's so close to 0 that it
Exactly, this is very close to 0. So even if you had YT minus 1, its effect is going to be small. So there is a process of using confidence intervals. So when we form an interval for the coefficient vector, and if 0 falls in that interval, we'll just drop that coefficient. So in this case, it is more than likely that that particular coefficient will become 0. So I was able to estimate the model properly. It happened so because my length of the series was 1024. If the length was, say, 256, there will be more error here. Good. So we had 1 equals P1 rho 1 plus P2 rho 2 plus sigma squared over gamma naught. Yes, sigma squared is the variance of the series, which in this case is 1, variance of the noise. So I can move these to the other side. So 1 minus P1 rho 1 minus P2 rho 2 equals sigma squared over gamma naught. Yes. If I flip on both sides, I will have 1 over 1 minus P1 rho 1, P2 rho 2 will be equal to gamma naught over sigma. So if we rearrange, we will simply have gamma naught is equal to sigma squared divided by 1 minus P1 rho Once again, you may say, well, why do we want to find the variance of the series? Again, variance is used to find confidence intervals. It helps in conducting hypothesis tests and so forth. So we need to know what the variance of the series is. So gamma naught would equal to 1 divided by 1 minus 3.1 0.002 times rho 1 0.022 minus phi 2.895 multiplied by 0.895. Plug it in and tell me what you get. We end up getting the variance of the series to be 5.033. Good. So this is why we did, the difference of ratings and so forth. So we can find the variance, coefficients, and so forth. This is great and all, but what if we want to express this series as an MA infinitive, right? So the roots of this particular model will lie outside the unit circle. In other words, we are trying to find the sideways. So we are going to use our model, which is yt equals 0.002 yt minus 1 minus 0.895. What was it plus? Yt minus 2 plus epsilon 2. Yes?
Why is it plus here?
What was our estimated model?
Oh, yeah, you're right, sorry.
So, which we can write it as lag multiplied by yt, lag squared multiplied by yt, plus epsilon t. Move the terms to one side, so we have yt minus 0.002 L. Yt minus 0.895 L squared yt equals epsilon t. Yt is a common. We don't want to use the letter L because it is an operator, so what did we do? We converted the wrote it in terms of set. What is that part called? The characteristic polynomial. And the notation is lowercase. We use uppercase for things. So uppercase for that. Good. Now we have to find the roots. The roots will definitely lie outside the unit circle. How do I know that? When I simulated the true model, everything went swimming, right? I didn't get it down. So it is a stationary series, so things are going to work out. How do we find the roots of that characteristic polynomial? According quadratic formula, let's quickly find the roots. Okay. So technically. This is not the repeating roots case. We actually have distinct roots. Right? One is 1.056, the other is minus 1.056.
Well, if you wanna go 3 decimal places, minus 1.058, but yeah.
Okay, so let's change the heading. It's actually distinct roots. My entire plan got ruined.
At least you didn't end up with complexing it.
And thirdly, the next example that I chose, that's repeating roots.
There were a lot of words.
Oh, well, I mean, it's a minor change, would be okay. When I do the video, I'll put it as distinct roots and I'll change it. The heading was wrong. Okay, so if we use the quadratic formula, the two roots are 1.058, 56. And the other one's negative 1.056.
No, negative 1.058.
What?
Negative 1.058.
For the second one?
Yeah.
Okay. So negative 1.058, a line outside a unit circle, so everything works out fine. Now, how do we find this phi weight?
Let's see.
The first we've got to find the lambda, then we have to find the c, which is why we focused a lot on difference equations at the beginning of the semester. So lambda 1 would simply be 1 over z1, lambda 2, 1 over z2, which is 0.99 something. We have 0.947 and negative 0.945. So we got the two lambdas, now we can find C1 and C2. What is C1? C1 is lambda 1 over lambda 1 minus lambda 2. C2 is minus lambda 2 divided by lambda 1 minus lambda 2. Correct? Think about the general pattern we have at the C values. I wrote that in class. That's how I remember it, is going with the general pattern. So 0.501, 0.499, things suggesting to work out and speed it. So we know what psi j is. Our general expression for psi j is C1 lambda 1 raised to j, C2 lambda 2 raised to j. So C1 is 0.501 multiplied by 0.947 raised to j. C2 0.499 multiplied by negative 0.945 raised to j. We can just plug in the values. How do we test if our answer is right?
The first should be 1.
What is best?
The row.
Row.
No. I cannot remember the name.
Pitchfork.
Pitchfork. Size 0 must be 1. So 0.501 multiplied by 0.947 raised to 0. 0.499 multiplied by negative 0.945 raised to 0. That term, just 1. If you add those two, you will get 1. In most cases, we're not going to get exactly 1, we'll get something close. Good. So we can find psi 1. Psi 1 is simply 0.501 raised multiplied by 0.947 raised 1. 0.499 multiplied by negative 0.945 raised 1. Typically, we can go for psi 1, psi 2, psi 3. In this case, it is going to decay pretty slowly. Can you tell me why? So typically the psi values will converge to 0. It's going to decay slowly.
Because the values that are being raised to the power of j, they're pretty close to 1 themselves.
Right, without using psi j in your explanation. From earlier today, that is my hint. It's not in the notes. It's what I showed you.
It's a thing.
It was the first one. Right, the autocorrelation function plot was going really, really slow. It was a slow decay. So when we convert, when we find the psi waves, all we try to do is take that A orbital, express it as an MA infinity, if we can. So in this case, we can. And when I find psi 2, what value would I, excuse me, psi 1, what do I get?
0.0029.
And let's find psi 2. Go ahead and find psi 2, psi 3, and psi 4 for me. Because once we do this, I'll show you how this relates to the plot. So same process, what I'm going to do, change the value of change. Psi naught is 1, psi 1, 0.0029, psi 2, I expect it to be bigger. Psi 3, I expect it to be smaller. Psi 4, I expect it to be bigger. Psi 2, 0.8949. 0.8949, psi 3, 0.0044. 0.0044, psi 4, 0.8009, 0.8009, and dot. Yes? Do you get the same thing?
Yes.
So now we have the psi values for the psi waves. I don't have to find every single one of them because we're doing it manually, but when we use computers, we can find all of these values right away. So, YT, when we write it in terms of MA infinity, the expression is psi naught plus psi 1 epsilon t minus 1, psi 2 epsilon t minus 2, psi 3 epsilon t minus 3, psi 4 epsilon t minus 4, plus dot, all the way up to you know, we throw in that side detail, epsilon z at the very end. Yes? So that's sine naught times epsilon z. Because the very first term would be epsilon z. So y t in our case would be epsilon t plus 0.0029 epsilon t minus 1 plus 0.8949 epsilon t minus 2, 0.0044 epsilon t minus 3, 0.8069 epsilon t minus 4. Dot, dot, dot.
8009.
Oh, 0.9. I can't even follow my own handwriting. And it's gonna keep on going. So we start with one low value, high value, low value, high value. And we sort of I expected this behavior. So in practice, you should be able to see it directly from the ACF plot, because when we are looking at an A series, we look at the ACF plot. If it is an AR series, we look at the PACF plot, because the PACF plot will get rid of the middle values and correlate, say, for instance, YT directly to YT minus 2, conditioning on values in the middle. So we need the ACF plot, and that is the ACF plot. You can say that's just one, right? Always. And that should be psi 1. Did we have a small value for psi 1?
Yes.
Yes, very small value. What was the value for psi 2?
0.895.
0.895, close to 0.9. Psi 3, really small. Psi 4, high. So it's going to go back and forth. Eventually, it will decay, right? So in this problem, is it a good idea to convert the AR series and express it as an MA infinity for modeling purposes? I would say no. The reason being that we call it the principle of parsimony. So anytime you build a model, you need to get an accurate model with fewer number of coefficients. So the AR part, we simply needed 2, right? Now, when I expand the AR part and represent it in terms of an MA infinity series, I end up getting a whole lot of coefficients. So the only way I would get an accurate answer is if I go past 30 weights, maybe 50 weights for me to get it. So I think let's step to the end. Landmarks. So let's just do landmarks. So you can sort of see a wiggly pattern, but you know, it keeps on going in terms of decay, right? And it'll probably take longer for it to completely decay and go to 0. So it is not a good idea to represent our AR series in terms of MA infinity. Does that make sense? Okay, so that is the distinct roots example. So now we we can move on to the repeating routes for real this
Oh,
time.
is it a real